welcome everyone to our seminar series. It's our great honor to have Professor Shipra Agrawal from Columbia University presenting today. Shipra is an associate professor at the Department of Industrial Engineering and Operations Research at Columbia. She's also affiliated with the Department of Computer Science and the Data Science Institute there. She got her PhD in computer science from Stanford University and was a researcher at Microsoft Research for a few years before joining Columbia. Her research spans several areas of optimization and machine learning, and she has made fundamental contributions to areas like multi-arm bandit, especially contextual bandit problems. Her research has received numerous awards, including funding support from the Google Faculty Research Award, the Amazon Research Award, and the National Science Foundation Career Award. Without further ado, I'll let Shipra get started. Shipra, welcome, and I'll let you get started.
Thank you, Jing and Hao, and everyone who helped organize this. It's a great pleasure to speak here, and I like the whole agenda of the seminar. So yeah, today I'm going to talk about this work on dynamic pricing and learning with Bayesian persuasion. So this work is fresh out of oven, like we are going to present it at NeurIPS in a couple of weeks. And my co-author Wei Tang is also on this call, who is a postdoc working with me, and he's actually on the job market. So if you have questions about anything technical, ask him. But yeah, it has been a great pleasure working with him on this. So let me get started. So what is this talk about? So I've been working on pricing a lot, and that pricing is often an important part of how you sell a product. So when you go and try to buy a product in an online marketplace, you see many things, and one of them is pricing. But there are many other things that you consider beyond pricing in order to buy the product. And that is some information that the seller chooses to reveal about the product. So here you see things like the cover page, you see the summary of the book over here. And the summary is something that let's consider. So the summary may not, some of this information is carefully chosen in order to persuade the buyer. In fact, something simple like a summary, which you might think has been picked up from the book directly, is often also carefully designed. So for example, here, this book was actually published before COVID, but you can see in the summary here that they mention COVID as one of the factors that influences our mental health and motivate the book in that way. So it's nothing wrong, like in some sense. There was something about how book summaries sometimes can be misleading because they are created, maybe not truly represent what the book is about. In this particular example, if you go through it, it's kind of harmless because they just talk about COVID-19 as one of the factors for which we need things like these. But in general, it could even be more misleading than that. And shoppers are often aware, more or less, about some of these embellishments that the sellers might be doing in order to persuade them. And this is common in other places, like, for example, the information that this hotel website is revealing is how many rooms are left at this price in order to make the buyer buy it quickly. And this, again, may be exactly the number of rooms left, or it might be something close to number of rooms. It might just be a reflection of how popular this hotel is. The number may not be exact, and often buyers are aware that you might book this hotel, and again you see only 5 rooms left, right? So it is possible. So in online newspapers, they would show you some headlines in order to make you subscribe to the newspaper. And these headlines are not wrong. They are not created for advertisement, but they are selectively picked out of the many hundreds of headlines they might have, or hundreds of articles they might have. They would pick selectively articles which might be more of a clickbait type, or might be something that the that would attract more attention, right? So overall, this information that is revealed in order for to have a good response, customer response, is carefully designed. It may or may not be exact reflection of the true information. And more than giving false information, it's often an embellishment or selective picking of the information available. Okay. So what we look at here is then think about what is the marketplace design problem at that point, right? So what we have here is that customers' decisions are being affected by what we characterize as three aspects. One is their own personal private preference, which is often hidden from the market maker. So market maker has some statistical ideas maybe, but doesn't know exactly what the customer wants. The product prices, which are decided by the platform, and what the information that is revealed, which is also decided by the platform. So here we have what we call in information design literature, a two-sided information asymmetry, where customers are also not completely informed because they only see what is advertised about the product and not everything that they want to know about the product. And they might have some idea of how the advertising is done. So we cannot assume that the customer is completely unaware of the fact that the advertised information is not the complete truth, right? And the platform doesn't know the user preferences. And both of them can learn about these things over time, right? So customers, when they see the advertised information, that allows them to update their belief about what the product quality might be. And again, I want to emphasize that we are not assuming that the customer will see that this product is the best product out there, and they will update their belief to believe that this is the best product out there, right? So they are aware that how advertising is done to some level, that when the advertiser says only 2 rooms are left, maybe a few rooms are left, not exactly 2, right? It's possible. So we assume that customers have some idea of how these signals are generated, and they have some prior belief about it. And based on that, they will update as they see these advertising signals. The platforms also can learn from the customers' responses. When the customers see these advertised information and they see the price, they respond based on their personal preferences and their utility functions. And the customers can learn from, the platform can learn about these preferences and utilities from their response. So overall, the kind of problem structure that we get, and I will make it more concrete once we define the customer behavior model, but the kind of learning and decision-making problem that we have is where we think about sequential interactions, like one by one, there are many customers coming and interacting with this marketplace. The platform is setting prices, and it's revealing some advertising signals, some information about the product at hand. And they observe the response of the customer to these price and advertisement, and which reveals something about, statistically at least, about the preference of the customers in this market. And based on that, they may update their prices or advertising over time. So the question that we are asking is, how should the platform dynamically set these prices and these advertising strategies in order to learn about the customers and thereby optimize the total revenue over time? So in order to make this problem more concrete, we need to define what exactly the customer behavior model here is. How do they update their preferences? How do they update their beliefs about the product when they see this advertising information? Before I go through that, anyone has any questions about the general motivation and setup? So I might also take breaks because my throat is not completely well today. I need to sip water. So feel free to ask questions. I will be happy for any interruptions. So the consumer behavior model, that exact model that we assume, is motivated by the idea of the Bayesian persuasion framework. So we have a Bayesian model of how customers update their beliefs. So we assume that, so some notation, so we have, let me just go forward. So we have product state is denoted by omega. So by product state, some representation of the true product quality or characteristics or how popular it is. So something about the product that would affect customers' response if they knew it. Now, this is the true product state, and this could be either binary, and binary state is actually a very popular setting in the Bayesian persuasion framework. So don't think about it as some kind of trivial setting. But we also think about more general where there's discrete number of m discrete possible product states. For example, it could be that it's only 2 rooms are left, or 3 rooms are left, or 4 rooms are left, so that kind of thing. Or it could be a continuous space as well. Now, the customer's private type, we denote it by theta, and in this talk, I will assume it's a single dimensional parameter, and it's generated, actually the type space doesn't really matter, but yeah, let's assume it's a single dimensional parameter, and it's coming from a distribution F, IID, which is not known to the platform. So now, how do the customers think about the product when they see advertising and they have their own preference theta? So it's defined by a value function, which is depends both on this type of customer. So for example, the customer type could be whether they like cheaper products, do the product color matter to them. So all those kind of things are in the type of the product, a type of the customer. And then there is the quality omega. So if the customer believes that the product is of quality omega, the way they would value the product is V theta omega. And in this talk, I will assume, just for simplicity, that V theta omega is simply theta plus omega. We can generalize this a little bit. In particular, we do need linearity in omega, but we are much more relaxed about the dependence on theta in the paper. So I'll mention the exact assumptions we need for the results later. But for simplicity, let's just assume the evaluation is theta plus omega. Okay. So how does the customer decide? So if the customer with type theta believes that the product state is omega, then they buy at price P if and only if the value function is more than their value of the product is more than the price. So this is a very standard way to think about customer response in terms of value function. And of course, the platform doesn't know theta, but it can influence omega, right? So it can influence the belief about what the product state is. So given this, how does the customer forms belief? So we assume there is a uniform, so by uniform, I mean, so let's not, by uniform, I mean everyone has the same prior. It's not uniform distribution. So there is a prior lambda on the product state. So this is a distribution. So for example, if we know that the products from this company are 90% very high quality and 10% not so good quality. So it's a uniform prior, which doesn't depend on this particular item. It's just in general, this is how customers believe the product from this company to be. So everyone has this prior when they begin with, when they have not seen any advertisements or any information about this particular product. So when they see a signal from the advertiser about this particular product, so for example, for this book, they might see a book summary. So that's the signal about how good this book or how interesting this book might be. So when they see a signal, they update this belief about, so they have a posterior belief, and this is updated in a Bayesian manner. So they think about how likely so if the true product quality was omega, then how likely they would be to see this particular signal given the advertiser's strategy of advertisement. So so for example, you assume, the intuitive way to think about why we assume that customers knows the signaling scheme is, so imagine that the customers knows that when the product is like good, the advertiser would say it's excellent, right? When it's bad, it would say it's nice. So suppose that the customer knows how the advertiser would say, or if there's only one room, or if there are 10 rooms left, the advertiser would say 1 room left, right? So the customer is aware that the signaling scheme, there is some kind of mapping from true state, not exact mapping, but there is a probabilistic mapping from the true state to the signal. So based on that, they will update their belief. So we assume that the signaling scheme, and for theoretical purposes, we assume it's fully known to the customer. Okay. In practice, you may have partial information about this scheme. So assuming this, we ask how should the platform should design this signaling scheme, assuming they will be fully known to the customer. So one reason for assuming this is that we don't want to assume that we don't want to think about how should the advertiser design the signaling scheme if they could completely hide behind it, like if they could basically dupe the customer. So we are assuming the customer knows the signaling scheme, they knows that they are embellishing, and then there could still be some advantage in terms of how to design this information, even if you are embellishing, how to embellish. So if you embellish too much, like if you say if your signaling scheme is that for every product, I will say this is the best out there, then it's not going to be useful, because when the customer tries to update their beliefs, they will basically get the same belief as the prior, because the signal is not giving any information, because for every product, the advertiser always says it's the best. So, but if you are a little bit more discerning and you distinguish between truly best products and not so good products when you're advertising, then that gives some information to the customer. Or if you always say there's only 1 room left, the customer is just going to ignore that information. So design of signaling scheme, even if you don't just reveal the product state, it's important to think about how much to reveal so that it does help you, but it doesn't completely become useless because you're advertising everything to be the best. So that's the question we are asking here. So the concrete problem goes like this, and I'll take a pause after I give this. So at time t equals 1 to t, so in capital T rounds, in each round, the platform first decides to post a price, PT, and it also at the same time announces the advertising scheme it's going to use. Or you can say that for some reason, everyone knows the advertising scheme that they're going to use. Then after the advertising scheme is fixed, the platform is going to see the actual product, what the product is, and based on the product, they will produce a scheme from this announced advertising scheme. And this signal is what the buyer with private type theta d is going to see along with the price. So buyer is going to see both the signal and the price, doesn't get to see the actual product state. So based on the signal and the knowledge of the advertising scheme, the buyer is going to form a posterior belief based on this posterior update. Okay, because they know this signaling scheme is basically by T, which has been revealed by the advertiser. And the buyer will buy the product if based on their posterior belief, so based on the expectation over their posterior belief, if their value is likely to be more than PT, the price. Okay, so based on what they believe, looking at the signal, what they believe the product quality or the product state to be, they will compute their expected value of the product, and then they will buy the product if that value is more than the price. And if they buy if they do decide to buy the product, if AT is 1, then the platform will get this revenue. So that's the overall structure. And the question is, how should the platform decide the price and the advertising schemes dynamically? So the platform doesn't get to decide the product state. All they get to decide is the advertising scheme. And based on that scheme, the signal will be generated. So they get to decide these 2 things in every round. And they don't know a priori what kind of buyers they're going to get. So over time, they want to learn about these distribution of buyer types from their responses. And the goal is to maximize total revenue. In particular, if you consider this problem, you would observe that every round in some sense is identical. in the sense that in every round you get a IID buyer of type F. You see a IID state product from this unknown from this known prior. And so if you think about what should be the optimal thing to do, if the platform knew the distribution F from which the type is arriving, they could actually find the optimal pricing scheme and the optimal price that they should be using all the time. So the only reason they're changing the price and changing the scheme here is because they want to learn. They want to explore different prices and different advertising schemes and learn what the optimal should be, because they don't know this distribution F. So if the platform knew everything, they would actually solve this problem of optimal revenue given this distribution of the buyer types, optimal expected revenue, and find a single advertising scheme and a single price. Our algorithm would instead try to explore different price and advertising schemes, and the regret will compare the two revenues. So any questions about the setup?
Yeah, sorry, can I have a quick question? Yeah, I was wondering, here, it seems that at every period, basically it's as if you assume that all the consumers have the same preference in terms of theta, the same type, right? Because it's a random variable, I understand, but when you say the revenue, it's PT times AT. It's not like a distribution of buyers with different types, but then a certain type above a certain threshold they buy. Not that kind of setting. It's basically at every period you have a representative buyer with a theta, realized theta, basically, right? Am I understanding this correctly?
So the platform cannot see this theta, and this theta is uncertain, like it's different for different time steps. It is generated from a common distribution, and so AT is a random variable.
Right. That I understand. I guess what I'm trying to get at is, in some other settings, basically for the same product that buyers buy, the buyers have different, like buyers with different types would buy the same product at a certain price, a single price, right? So here, from what I understood, all the buyers have the same type. It's just a random variable at certain t, right? Of course, at different time periods, yeah, the type can be different, right? So because you're a
buyer coming from a pool of buyers in every time step, and that buyer looks at the product offered and decides whether they want to buy it or not. So it's not a contextual setting. I don't know if that's what you're referring to. So the preference doesn't depend on the product, because they don't know everything about the product. So it's single type of product as well. It's a single type of product. It's just different products from that type.
Yeah. So for the product, I understood. So for the buyers, yeah. So I guess what you're saying is kind of what I'm getting at, which is for a product at a certain time period, basically, all the buyers buy, like the buyers with a certain theta would buy, and basically it's a representative buyer at this period. It's not like it's not like 10 people buy the same product and 10 of them have different thetas, right? It's the same theta at the same period, basically. So
at one period there is only one buyer. You can think about it like that. So we are thinking of buyers as one by one, coming one by one.
Yeah, so I get it. And the second question is, does it matter if the platform announces and commits to the the signaling scheme before or after the posting the price? The sequence doesn't matter?
No. within price and this, it doesn't matter, but they have to commit to it before seeing the products. So they cannot decide the scheme based on every product.
Oh, yeah, of course, that I understand. Yeah, thanks. Yeah, thank you.
Any other questions?
And just some quick clarification question. Is the time horizon T fixed, or it's like something that you're gonna prove regret based on?
I think it's like usual bandit kind of thing where if it is going to be based on how much time you have, regret will be based on that. I think it should be possible to make it any time, like where you don't need to know it in advance, but I'm not sure if we did that in the current paper, if we paid attention to that in the current paper.
I see. And in this current formulation, there's no learning happening on the customer side, right? So the learning is only for the platform.
So in some sense, it is happening if you call Bayesian learning kind of thing. But you are right that because the buyers are changing every time step, they're just doing one Bayesian update. That's all. Yeah, you're right.
I see.
The buyers are not long term. They're not forward looking because they're myopic. They just come and they go.
Okay.
Every time step there is a new buyer. Yes, that's a good point. Yeah.
I guess one thing, if the platform is allowed to actually change in the signaling scheme with time as well, how would customer actually? Yeah. So sorry, I was connecting this to practice.
Okay.
If they're allowed to change the signaling.
Yeah, so I agree. Like in practice, you would think of this change as not so. This is like a slow change, and hopefully we can even put a condition that this shouldn't be too many changes here. This is more so that the seller is adjusting based on their learning. So maybe it's more of think of this as a more long-term thing. Like after having enough samples, they can say, "Oh, I think I'm advertising too aggressively. Let me bring it down a little bit." So think about this as that's why in theory we are saying it needs to announce it, but in practice it should be slow enough change so that it cannot hide it. Over time they will know, because in the end, like the optimal is a fixed one, so you would be converging to a fixed one over time.
Thank you.
Yeah, that's a good question. Any other questions? Okay, so I want to just point out some connections to existing literature. So obviously this whole setup is rooted in dynamic pricing. So I think of this problem as adding one more control to the platform or the seller, where in addition to deciding the price, they also want to think about how does this price interact with the information. And basically by revealing more information, can we actually persuade the customer even at a higher price, or if we don't give enough information, do we need to lower the price? So that kind of interaction between advertising and pricing. And in fact, this is also motivated by some studies in marketing that show that advertising is not just about bringing attention, it's also about providing signals to the about the product. So information design is an important component of advertising. How much information it reveals can matter, especially online, because online, like people are a little bit more, they read things, like they would read the summary, they will read the how much rooms are left. So if there is a little bit more attention you can capture online and reveal information. And then the connection of advertising and information then brings us to the information design setting, where Bayesian persuasion, there's a lot of tradition in working on Bayesian setting here. And the work, we build upon that framework. In fact, we will use some results from Bayesian persuasion settings. And there, one big difference is that there has been very little work which looks at the case where the platform or the person designing the information doesn't know about customer preferences. So there usually the assumption is that how should the information be designed when you know the customer preferences, like the type theta here is known. There is some work though, although they're not exactly the kind of uncertainty we assume here. So the work here assumes, which is also Wei Tang is also one of the co-authors here, and they assume here that the customer preference is not known, but it is fixed. There's no uncertainty, like there's no distribution. It's not changing over time. So you need to search. So they give like a binary search kind of algorithms to search for the customer type. And some other work here assume full information settings where the customer preference is changing, but it is revealed, and so on. So this is the first work which considers this kind of uncertain preferences, which is very common in dynamic pricing. Like in dynamic pricing and learning, it's very common, and bandit problems is very common to have this preferences which are stochastic and uncertain and IID over time. But in Bayesian persuasion framework, this is new. So this kind of combines this bandit dynamic pricing kind of literature with the Bayesian persuasion literature. So what are our main results? So our main result, I summarize it here, and this is stated more generally than what I will actually talk about today. So for finite state space, when their number of product states are m, we show that we can get a regret bound of t raised to 2 by 3, m raised to 1 by 3. So for binary signals, for example, it's just t raised to 2 by 3. And to see like whether it's tight or not, so before that, upper bound actually holds for any type distribution. So one remarkable thing here compared to existing work is that we don't make any assumptions about any Lipschitz property of this type distribution or any kind of assumption of how nice this distribution is. So it's more in the line with dynamic pricing literature where you don't usually make such assumptions. We assume linear value function. That's one critical assumption we have. In particular, we have to assume that's linear in product space. So that's crucial. We can relax the linearity on theta, the type space. In particular, we can handle any Lipschitz monotone type function, value functions in type space, but we do need linearity in product space. And you will see why when I describe the algorithm. And lower bound actually of t raised to 2 by 3 follows from dynamic pricing. So if you think about a special case of our setting is when the prior, for example, is a point distribution. So basically imagine that the prior already reveals the product state, right? So if the prior, you already know what the product is exactly, and there's nothing to be known, then there is nothing to be gained from advertising in our framework. And in which case the problem just becomes a dynamic pricing problem. And since we handle any type of prior, dynamic pricing and learning problem is a special case of this problem. And there's a well-known lower bound of t raised to 2 by 3. So for a finite number of states, we are very close to the lower bound on this problem. For continuous signal space, we do have t raised to 3 by 4 as an upper bound. Right. So before I go to the algorithms, any question about the results?
I don't know if you will talk about this later, but can you give some intuition about the gap between the finite support case and the continuous case?
Maybe at the end of the talk. Yeah, I don't have I can tell you where it's coming from, but I don't know about yeah. Maybe once we have the algorithm. I don't know what's tight. That's what I mean. Like what is the tight bound? Okay, so algorithm design analysis. So let's first discuss what is the challenges in this problem? And I will kind of build upon saying that suppose we already have solved the dynamic pricing and learning problem, right? So for dynamic pricing and learning, we know how to get the lower bounds. There are algorithms where you don't know the customer preference, exactly the same model as us. And the lower bound is t raised to 2 by 3. The upper bound is also t raised to 2 by 3 in order sense. So what is the difficulty beyond that in this problem? Why can't we just use that? So here we are deciding, first of all, we are deciding both price and a signaling strategy. And why this makes things complicated is it's a very high dimensional decision space now, right? So we are deciding a signaling strategy, which is all mappings from the product space to the signal space. And in fact, we don't restrict signal space. It can be anything, but it is at least a big enough signal space so that you have exponentially many possibilities of doing this. So one first observation that we make, and this is not our work, has been observed in Bayesian persuasion framework, that because of the linearity in the product quality of the value function, we can actually reduce our problem, that instead of picking a advertising strategy, you can actually just effectively what the advertiser is doing is picking a distribution over posterior means. And this is not very hard to observe. So we assume linearity in omega. And in particular, let's just assume that B theta omega is theta plus omega. The observations will follow just from linearity in omega. But if you look at that, then the customer is buying based on this comparison. And in this comparison, the expected valuation actually only depends on the expected valuation of the product state on the posterior belief. So what you're deciding, what the platform is deciding by deciding this strategy is really deciding what this posterior belief will be. Because the prior belief is lambda, which is known to everybody. But once you decide the advertising strategy, you are deciding the posterior belief, what the posterior belief is going to be. So when you're making the decision about pi t, the platform is really making a decision about the posterior distribution. In fact, the mean of this posterior distribution of this mean. Okay. And the only trouble is that you cannot choose any distribution over these posterior means. So we denote by phi t, the phi t, the distribution over the posterior means. Okay. So the posterior mean is distribution depends on the distribution of the signal, which depends on the distribution of the product, which depends on the prior distribution. So by deciding the advertising strategy, you are deciding this phi t, but you cannot just arbitrarily pick it. You need to make sure that it is a feasible distribution over posterior mean. So every posterior mean generated from this distribution has to be from the posterior of the actual some signaling strategy that is feasible. And luckily, we already know how to define the space of these feasible distribution, and this is coming from Bayesian persuasion work. And there's a Bayesian consistency condition derived in this paper, which shows that any phi that satisfies these complicated looking conditions is actually a possible distribution for which you can come up with a signaling strategy such that this will be the mean distribution. Okay, so what that does is it makes the problem a little bit simpler. Instead of picking all these strategies in addition to price, you're picking the distribution over posterior means. So you're just picking a distribution over one-dimensional object. Okay. And then you do the same thing. Given the posterior mean distribution, there's also a way to go back and say what is a signaling strategy pi t that will give you this distribution. And so that construction is in that paper. I'm not going to repeat that. So this is actually constructive. So you can go from here to pi t. And based on this pi t, the platform will, as before, give a signal. The buyer will take that signal and make a decision based on that signal. And you would be guaranteed that the buyer decision is same as saying, make a decision based on the posterior mean sampled from this PT. So this construction will ensure that. So what we have done here is we have reduced the problem to deciding price and the distribution over posterior means. Okay, so it's slightly simpler because it's now so you have to decide a one-dimensional object and a distribution over another one-dimensional object. So it's slightly simple decision space. It's not still simple enough. So we might say since you have only two things to decide, PT and VT, why not use something like a Lipschitz-Bandit algorithm with 2-dimension and so on. So the thing is that this is not a 2-dimensional decision. You have to deciding this distribution, and this distribution needs to satisfy this complicated Bayes consistency condition. So you cannot just use a Lipschitz-Bandit algorithm, and you don't have any Lipschitz conditions on this decision. So even if those algorithms work, they will not give you t raised to 2 by 3, first of all, because Lipschitz-Bandit with two decisions has regret of order to t raised to 3 by 4. With one decision, it's t raised to 2 by 3, which you get for dynamic pricing. So even if they work, they won't give you the regret we want, but already they don't work because this decision is not a simple one-dimensional decision that you're making. Okay. So what we do here is we kind of get away from this idea of black box exploration of two decisions versus one decision. We say that what changed from pricing is the decisions, but what did not change is the uncertainty space. So in pricing, you had an uncertainty space of one dimension, and we still have an uncertainty space of one dimension. What we don't know is the same. What we don't know is this demand distribution. We don't know what is the distribution of theta, which decides the distribution of like how the customer compares the value to the price. Okay, so in particular, what we know is that the customer makes the decision based on this. Okay, after we realize that the signaling strategy only matters up to the posterior mean, we know that the customer decides based on the value at their theta and the given posterior mean. They decide whether it's greater than the given price or not. Now, if you look at this thing over here, if we realize that the value function is simply theta plus q in the simple setting, then the customer is simply deciding whether theta is greater than p minus q or not. Okay, which is basically they are deciding whose probability is this. Okay, it's 1 minus f theta. Sorry, f. So this probability of theta greater than p minus q is 1 minus f p minus q, which we denote as the demand function. Okay, so in order to know whether the customer will buy at price p and given the posterior mean q, we just need to know this demand function d. So if you know the demand function, we would actually know the entire revenue expectation, which is given by p times the demand function of p minus q. So what we do is we will say that we ultimately look, like I'm assuming most of you know about the optimistic estimation in bandits and so on. So if you think about UCB algorithm, which works on the idea of optimistically estimating your objective function and making decision using the optimistic estimates, then if I think about how can I optimistically overestimate revenue, then the only unknown here is this demand function over here. So what I will do is I'll simply estimate this demand function at different points. Okay, and hopefully p minus q will be one of those points for the q that I want to offer. So I will overestimate the demand function d by DUCB, and that will give me a revenue function which is overestimated estimation of the true revenue function for any price p and q, p and signaling strategy phi. So before we go into difficulties of doing that, what would the algorithm look like if I do that? So the algorithm would be, I have some way of keeping a discretized type space on which I will keep the estimation, I will keep the estimated DUCB, the demand function. Okay, so I will keep for every point in this space, I will keep this demand function. And that will allow me, hopefully, if this space is good enough, if it is fine enough, that will give me a good estimation of the revenue function, because in the revenue function, I have to estimate demand at this points p minus q, which I'm hoping it's in this discretized space, in this S space, which is a discretized version of the type space. So if I can make this S fine enough, I will have a good estimation, overestimation of the revenue function. And then I will go through, I will find the price and fee, these distribution of posterior means that optimizes this overestimate. So my overestimate will be optimized, my optimistic estimate will be optimized by my offered price and the distribution over posterior mean. And this is very similar to your general UCB algorithm. And then based on that, I will offer a signal, the customer will respond based on the true demand function. Okay? So the customer's decision will depend on the true demand function. Now, when I observe that, so I'm observing a decision from the true demand function, I should use that to update my estimate of the demand function. So I will observe the true demand function at this point, P minus Q. So I'll have to round that to my discretized space and update the estimate of the demand function at that point. So what the platform needs to do is to offer price and the distribution over posterior means, QT, in a way that the points at which you observe these demand functions give you knowledge about this demand function at points where you didn't know about it. So this is the only way it can explore the demand space, the demand distribution. It cannot just say, let me learn that the customer responds at this point and that point. The only way to control this learning is through price and the posterior mean. So this points to the difficulty in generating this demand, this discretized space. I cannot just uniformly have a uniform grid over the type space, even though it's a one-dimensional space. The trouble is, if I just create a uniform grid over this space, I cannot explore that uniform grid because this QT has to satisfy, the distribution of QT has to satisfy this complicated Bayesian consistency condition. So I cannot arbitrarily generate any point in this space and ask the customer about that. I need to make sure that the phi that satisfies Bayesian consistency condition generates a QT such that PT minus QT is the point that I want to explore. Okay, so that's why we need, one of the main challenges and the main contributions of the algorithm was to come up with a good way of discretizing this type space in a way that allows me to explore these types, the discretized type space effectively by generating PT and QT, the price and the posterior mean. And this has to be done while there is no Lipschitz condition assumed. So you have to make sure that you explore enough. You cannot just say, if I explore within epsilon, I will get Lipschitz factor of this much. So I will not go through the rounding scheme completely, but there are two components of this discretization. One, you have to discretize in an intelligent way. And then when you get a point like PT minus QT, you have to do rounding in an intelligent way. And the rounding is, so first of all, what is our grid? Our grid is through discretizing both price and the posterior mean. So first we discretize the price and then the uniform epsilon grid. Then we discretize the type space with an epsilon grid, and we add all possible P minus omegas because P minus Q is what we are trying to explore. So for every signal, every product state, we add these points to the space. But just discretization is not enough. We want also a scheme like a phi such that we generate points in this space. We cannot just directly ask customer about a P minus Q in this space. We have to generate phi t in a way that Q will be in this space, that P minus Q will be in this space. And one of the main theorems, technical theorems in the paper is to show that we can in fact generate a feasible advertising strategy such that the output of, so if you have a P and phi, you can round it to a P dagger and phi dagger in a way that your posterior mean will lie in this space, the P minus Q from this will lie in this space, and the change in the revenue function is at most 2 epsilon. Okay, so there's not much loss of revenue in generating these schemes, right? And once we do that, then the rest of the theorem is pretty much your standard bandit algorithm. So we go through the same steps of people who have seen banded proofs, you say that, oh, optimal revenue can be upper bounded by the UCB estimation. But here, because we do rounding, we cannot upper bound, but we can only upper bound within 2 epsilon. And then you say that you have this, how much do you overestimate the revenue can be bounded, and that sums to the number of discretized points, square root number of discretized points times t. And here is where the size of this grid matters. And that's where this number of states come in, because you remember we had to add all these points for every product state. We had to add the difference of p minus omega. So that's where the m comes from. Okay. So this is how you get the regret bound that we have with the dependence on m. So this is just to, I don't expect you to be able to write the proof now, but I hope you got like some gist of where the different components of the regret bound are coming from, especially if you have seen banded proofs earlier. So just to summarize, we introduce a joint dynamic pricing and advertising problem with uncertain demand learning. And particularly what was exciting was to think about this Bayesian persuasion framework, which is a very nice way to think about how customers might update their belief, given that they know that it's not the actual product space, it's some kind of modification of that. And they know how the advertiser might modify the true state. And we show that we almost get the same regret as what the dynamic pricing without advertising would be, at least in the case where the number of product states is finite. There are many, many interesting directions, and some of you actually in questions were asking about them, and I invite Jesse's questions to be related to this. So for example, you could ask, what if the advertising was personalized, right? So right now we assume that the advertising is decided even before the customer arrives, right? So the advertiser decides this will be my book summary, right? For anybody who comes. So it's only based on the product they see in front of them, not based on the customer who is coming. But in general, you can also personalize the advertisement to the customer who is coming, and it is done in practice. So how we believe that this should be related to, so right now what we were doing was something like regular bandits, and this would add something like contextual bandits to the mix. The other interesting thing is, what if advertisement involves some pricing information? So this is something very interesting to us because we have been also working on reference price settings separately from this way, as has been, and I have an upcoming paper about how to price if the customers know that the price is lower compared to the past prices or it's higher compared to the past prices. So if they are more long-term, if they learn about your pricing strategies over time, then what happens? And now this is very interesting with advertising, because in general, customers may not remember what the price was earlier, but often advertisements do tell them about it. Like here, they're saying prices are currently low, they're likely to go up in next 5 days. Here, like this is actually my personal Thanksgiving experience, where even after I bought it, they would keep telling me that the prices are very low and they will go up later compared to the regular price. So this is somehow informing the customer to update their reference, right? So they're saying the reference was 68 and now it's 25. So even if the customer was not likely to consider the reference price, it's making them aware. So advertising can somehow change how much reference price is taken into account by the customer. And this is very interesting because it changes which model you are in. So based on how you are advertised, the customers might act myopic or not history aware. But if you make them aware, they can act like as if they know the reference price. So this would be another interesting direction to explore. So that's my talk, and I am happy to take questions.